there are many practical applications in which there is not just one actuator, but two, right? So in this particular case, for instance, I am just to give you an example, I consider the situation where the dimension of the system is capital N. I'm sorry, I changed notation a little bit from the previous slides where it was small n, but this is a finite dimensional system. Of course, everything I'm talking here, you can do it also in the infinite dimensional case, right? But then it's more technical, in particular because you have to discuss the different kinds of semigroups one is generating, right? And then I am considering the situation where you have two actuators, right? So B1 and B2, so Bj will be vectors in Rn, right? So these are like two compressors, two engines, two actuators that you can manipulate in order to guide the whole system. As I said yesterday, one of the analogies in the context of machine learning is federated learning, right? Where two different groups of people, right, are cooperating in order to generate, for instance, a neural network that is able to interpolate and generalize well data, right, on a given topic on which each of them have partial information, right? So you, for instance, try to discuss behavior of people. One person has data according to gender, another group has data according to ages, right? And then both of them are trying to, build a neural network that is trying to anticipate the behavior of people, both according to gender and age, right? So here is a little bit the same. You could say, well, so here now I have two controls, right? So I have two controllers, two actuators, B1 and B2. Each of them is acting differently on the system. It could be like, like two laser beams acting in different directions, and you can just regulate the intensity of each of them. So the controls are U1 and U2, right? Both depend on time and both are scalar. So when you look to the problem that way, you say, well, there is nothing new on it, right? Because I could simply say that all this, right? I could write all this as being, right? As being some B and then some vector U, where the matrix B now is n times 2, right? And it's a matrix with two column vectors, B1 and B2. And then the control U tilde will be a vector with the two scalar controls U1t and U2t. Right? So then you say there is nothing new here. You could simply, apply Kalman rank condition and determine whether A, B fulfill Kalman, and that will be the condition for controllability. Yeah, that is true. But in many practical applications, right, you can be in such a situation in which you don't want to use both controls simultaneously, right? So you like to use first one and then the other. So for instance, this is what typically on hybrid cars you expect to do. You use either gasoline or you use electricity, right? Okay, you can of course use a combination of both, but let us consider the extremal case in which you either use one or the other, right? So this is like when you are playing ping pong or tennis, so one kicks and then the other one kicks, but not both of them are kicking simultaneously, right? This is a typical application. So the question is then, right? The question is, even if AB in such a context is controllable, can we control the system so that U1t times U2t is equal to 0, right? So what does it mean, the fact that U1t times U2t is equal to 0? It means that either U1 or U2 or both are equal to 0. So it means that you never, in any time instance, you are not using the two controls simultaneously, right? You are either using one or the other, or simply doing nothing in case that, there is no need of action. Okay, so this is a switching control system, because I am switching from U1 to U2. And as I said, in the context of reinforcement learning, when, two different groups are cooperating in order to build, a neural network that is interpolating and generalizing data properly, right? You want this to happen also in that alternating manner, in that switching manner, in particular because they are not allowed to hybridize, to mix data, right? So each control has to act on the system with the information the control can perceive, right? Okay, good. So in practice, switching systems appear in many different applications. So for instance, in many applications, like medical, when a human takes a given drug, right? Then in some sense, the physical, say, system of the human, right? Overall physiological system behaves differently. So it is, or also when you are driving, your bicycle or your engine, and you change the gear, you realize that once you change the gear, you go from one velocity to another configuration, then the dynamics of the engine is also changing. So in real applications, one should consider even more complicated cases where, depending on whether U1 or U2 is acting, you should also consider a dynamics A1 or A2, right? So this is a simplified situation in which I am assuming that the dynamics is given, right? The dynamics is unique, right? And then you are only, acting on it with one engine or the other, right? So this could be the case of the heating system of the office building in Jilin we were considering, right, yesterday, that office building. And then we said, okay, the system of, the heating system, the connectivity of the offices is given, and this gives me the diffusion, say, the heat diffusion process, or the cool air diffusing process, the air diffusing in the building is given by this free system. But I have two different engines in order to pump in either, heat or cool air, right? But the system doesn't really change. But I insist this is a simplified model, because in many applications, right, whenever you act with one controller or the other, you should also jump on the operator A. And this is a much more complicated case, because then the action on the control on the system is nonlinear, right? So this could be the case where, this will be the case where I'm trying to write something down. Okay, so let me see, how can I do it? I think I can here add a page. Okay, good. Okay, I can add this page. So you could also consider the case where, for instance, the control, right, is acting, right? So maybe, okay, so you could also consider the case where the control, right, is acting on the system that way, where AT is either A1 or A2, right? Okay, so that, sometimes the system is given by A1, right, for some time intervals, right? And then A2 in another time interval, right? This will be a different situation. Then, even though this is also a switching system, right, the control of that system will be much more tricky, because then the relation between the control and the state will be nonlinear. Okay, so here I go back to the situation we are considering. This is the classical case where I insist the dynamics is given, it doesn't switch, and only the controls are switching. Okay, so what is the difficulty for doing this? As I said before, right, if the question is simply to understand whether two controls can simultaneously control the system, then this is something we know. It's just Kalman for B, the matrix containing the two vectors B1, B2, right? So if you really allow two groups to fully cooperate, exchange information, right, in the context of neural networks that I was considering for interpolating data, if the two groups can share all the information and they can act simultaneously, you don't need to think on two groups. You can just put all the information in one group and allow this one group, you know, to operate on the neural network simultaneously, right? So this goes back to the original problem I mentioned the other day. So questions become much more tricky, for instance, in those problems of classifying data, right? Right? If, you know, we were considering these problems where I have to, you know, given data that are mixed, right? I needed to build a neural network, right? Allowing me to guarantee that the red points go to the upper hemisphere and the blue points, right, go to the southern hemisphere in such a clear classification procedure. If I have two different groups, right, allowing, you know, allowed to have all the full picture, observe the full configuration, and act simultaneously. So I don't need to consider the case that I have really two controls. I could just think that the two of them are cooperating, and there is one single actuator that with full information is able to take decisions about what, you know, one can do, right? In particular, I could take this point and put it here and take this blue point and put it there, right? The question is much more tricky if we say that in such a case, you know, one group is seeing some data and the other group is seeing other data, and therefore, you know, their actions can be somehow partial, not, you know, have complete information on the system and not be able to deliver the task unless they cooperate in a smart manner, right? Okay. So, but then, as I said, this paradigm is more related to the situation in which I say, okay, fine, there are two controllers, but they cannot control simultaneously. One is acting and the other one has to wait until the action of the other one has finished, so to intervene, right? And vice versa. When the second one stops, then the first one can enter in action. So this is the typical situation we expect, right? Where we have a blue control that is acting during a time interval, and then only after the action of this first control has finished, then the second one will enter. And of course, this can be repeated again and again until the task is achieved. So you see, you were considering the case, I go back to the classical case where you had, you know, the two controls acting simultaneously. This is the functional we will need to manipulate on the adjoint system. The adjoint, of course, is given by the, you know, by the matrix A, the adjoint of A, right? There is never control on the adjoint. And this is the matrix the quadratic function I should minimize in order to achieve the controls, right? So we know that the controls will be just given by the minimizing this functional, in which now both B1 and B2 are active. B1 is giving you one projection of the adjoint state, B2 the other projection. I add the Euclidean norm of both of them, right? So x1, so here is xt is the target, x0 is the initial datum to minimize. If I have the Kalman rank condition, I know that I have the observability. I know this functional is coercive. I can minimize it, and I know that the minimizer of that functional, right, will give me a specific, very particular solution of that problem, right? And this solution will give me the controls, right? The control being given, you remember that E1 will be simply the B1 times phi hat, and U2 will be B2 times phi hat for the minimizer, okay? But of course, when you do this, nothing prevents, right, that both controls are acting simultaneously. They will be active all the time, and you will get one that is really oscillating according to, you know, the projection B1 of phi, and the other one that is having a different dynamics, but both of them will be simultaneously active, right? And this, of course, is more expensive in the sense that I'm not enjoying of the possibility that while one person is working, the other one is resting, so to recover forces. So this is one hand. And on the other hand, they have to work simultaneously. And you know, when you work simultaneously, things are tricky, right? So this is why we need these special editors when we are writing a paper where two different people can be writing simultaneously. Otherwise, it can be confusing, right? So the traditional way of writing a joint paper is that, okay, you please write your draft, you send it to me, I read it, I operate on it, and after a few days, I send you back and we iterate until we are both satisfied with the manuscript, right? So doing it simultaneously is more tricky, right? Because while one is changing remark 3, the other one might be changing theorem 1, and actually the remark 3 was referring to the theorem 1 in the previous version, and one has to be particularly careful that in the end, the results are coherent, right? So otherwise, you could end up with an article where there is the statement of a theorem, and then the proof corresponds to a different version of the theorem, right? Okay, so the sequential manner, the traditional manner in that sense is safer, although it might be slower, right? Because at each time instance, only one of the cooperators is working on the manuscript. Okay, so how can I, you know, how can I make that the controls cooperate? Okay, so how can I, when I am dealing with an optimization problem, a control problem, or a machine learning problem, where there are two teams operating, how can I make, you know, their work to be, you know, programmed in a switching manner? Well, you could decide that a priori, right? So you could, for instance, take the time interval 0 capital T, right, and divide the time interval from 0 to capital T into pieces, right? And then simply say, in the first one, the red control will be acting. In the second one, the blue will be acting. In the third one, it will be red again. In the fourth one, it will be blue, and so on, right? We could do that. And we could change these, say, sub-intervals in a totally independent manner, right? Not necessarily on a uniform mesh, right? So this could be an arbitrary mesh, and as many switchings as you like, right? So let me take here two n switchings. This n has nothing to do with the dimension of the problem, so let me call it P. Right? So I just take a partition of the interval, and then I say, in a totally arbitrary manner, I say here the control will be red, and here the control will be blue. Okay? So how do I succeed controlling a system in which a priori I was told, okay, this is the scheduling, right? This is like, you know, you are delivering a course with a colleague, and then we have already a priori, we have decided, you know, that I will be talking on Saturday, but my colleague will talking to you on Monday, and then I will do it on Tuesday again. And then Wednesday and Thursday will be my colleague, and then I will take over again on next Friday or so, right? So you have an a priori planning, like when you are running a workshop and you have different mini courses or different lectures, and you are doing an Excel planning, a calendar, okay? So this is what we do. We do an a priori planning. How is this reflected on the way I should build the optimal control? Well, it's very simple. I take this partition tau, and out of this partition, I build the corresponding functional to be minimized, where again, xt is the target, right? X0 is the initial datum. So this could also, be totally valid for these problems in supervised learning where I have data X0 and I have targets X capital T, right? And then I say, because the two engines I don't want them to be working simultaneously. I want to be working in a switching manner, alternating, cooperating, but alternating. Then according to this partition, the decision that was made was that, the B1 observer, right, the sensor B1 will only measure information on, the red intervals, subintervals here, while, the blue one, so this should be P, right? The blue one will be reading information in the blue intervals, right? So here the red intervals and here the blue intervals. Okay, so now what is the difficulty with respect to the previous functional? Well, of course, the difficulty when minimizing this functional is that the functional is less coercive, right? So I was before minimizing the same functional, but the two quantities were integrated from 0 to capital T. So now I have basically half of the information only. So, the quadratic form here is much weaker because I am not at any time instance, I'm not adding, the two projections. I have either one or the other, but never both of them. Now, the question is, can I guarantee that this functional is still coercive? Well, I apply the same principle as yesterday. We said, well, in order to show that there is a minimizer, the minimizer will give me the switching control with an a priori pre-designed switching pattern. In order to do that, I have to show that this functional is coercive. For this, I have to show, the only thing I need to show is that there is a unique continuation property telling me that if there is a solution phi of the adjoint system, so that B1 phi is 0 in the red subintervals, and B2 phi is 0 in the blue subintervals, then the solution has to be identically equal to 0. Can I do that? Yes, in this case I can. Why? Because the system is finite dimensional. Therefore, the solutions phi are analytic in time. So this will apply also for analytic semigroups like parabolic equations, the heat equation, for instance. So if B1 phi is equal to 0 in the red subintervals, it has to be 0 everywhere because the only analytic function vanishing on a time subinterval is the 0, 1, right? This is the analyticity. Say infinity doesn't suffice, right? So recall yesterday I told you, I warn you, so don't never buy a ticket, right, of someone promising you an analytically smooth takeoff of the airplane, right? Because an airplane that is analytic will never be able to take off, right? It will continue, on the floor, right? In order to take off, you need to generate a function like this, which is going to be say infinity, right? But it will never be analytic, right? C omega will never be analytic. Okay, but these functions are analytic because they are the solutions of a linear constant coefficient ODE. And therefore, as soon as B1 phi and or B2 phi is equal to 0 in some subinterval, is 0 everywhere. But once they are 0 everywhere, this is, like in the Kalman-Rank condition, when the full matrix B applied to phi, B star applied to phi is equal to 0. And because of the Kalman-Rank condition, that is done. Okay, so then you see, you can pre-program the switching pattern and you will know that you are able to control the system. So this is an interesting point, right? So whenever for a finite dimensional or more generally a semigroup that is time analytic, whenever two controls simultaneously are able to control the system, you can also say, okay, fine, I don't want to generate too much fatigue, and I can alternate, and I am totally free to choose, the switching pattern I like. Okay, you can do that, fine. But then I will ask you, if you tell me about this result, I will ask you, yes, but what is the optimal switching pattern? Right? So maybe you decided to, to switch equally, to take a uniform grid and switch, alternating one and the other, one and the other, so that the load of any of them in terms of the time duration of the work is identical. But maybe one of them maybe is more efficient than the other. When two people are cooperating on a physical task, you realize, oh, we were planning to do it, both of us, but I realized the other person is better fit to that task, so is more efficient, while more tired and less effective. So in view of this, you could wonder, what is the optimal assignment of tasks to the two actuators that are cooperating for, the ultimate goal, right? If you want to really get an optimal distribution of tasks, what you need to do is that rather than, minimizing a functional J in which the task was allocated to each player, to each actuator a priori, without having a clear reason justifying this a priori distribution of tasks, right? What I will do rather is to say, okay, let me define the new functional JS, S for switching, so that what I do in the time interval 0 capital T, I will just, integrate the maximum of both of them, right? So these are the two observed projections on the adjoint system. In the original classical case, I add them both and then the two controls are acting simultaneously. In the a priori planified switching pattern, right? I have, split the time interval a priori in some subintervals for B1 and some other subintervals for B2. But now, because I don't know whether the a priori chosen switching pattern is optimal, what I do is I will take the max of each of them, right? So that now when I integrate this from 0 to capital T and I take the maximum of both of them, right? When you observe the switching pattern, you realize that the switching pattern might depend on the adjoint phi you are integrating, right? Because whenever you change the datum phi 0 for phi and you compute a new solution, how, the two projections, one could be this one, right? This could be B1 phi, and the other one will be something like this, right? B2 phi, right? From the perspective of the absolute value, how, right? The maximum we'll achieve will very much depend on this relation between, the red projection and the blue projection. That depends, of course, on the initial datum, right? There could be initial data for which you could think on a spectral decomposition of phi into the eigenvectors of A. If B1 and B2 were eigenvectors, you could see, for instance, that there will be solutions in which, one component is very active while the other one is basically zero, or the reverse, right? So thinking on this kind of spectral decomposition and the interactions of B1 and B2 with the eigenvectors of A, you can easily build examples where all kind of possibilities could arise. You could also make it, so that they are both equal. But generically, normally, one will be bigger than the other. So what is then the switching pattern you will get? Well, it's very clear, right? The switching pattern you will get in this case is that I will be able to minimize this functional. And when I write the Euler-Lagrange equations of that system, what are you going to see? Well, what you are going to see is that whenever in the minimizer, the absolute value of the first one is bigger than the absolute value of the second one, by continuity, whenever this happens for a time t, this will happen on an interval, you will differentiate the integral over that subinterval, and what you will get is that, of course, while this one is bigger than this other one, the max is simply the first one, and therefore when you linearize, you are linearizing this quadratic term, and therefore the control is given by the B1 projection. While when you are in the second one, right, when you are in the second one, in which the second component is dominating the first one, for the same reason, the control will be given by the second one, right? But you see that now, in this switching pattern, right, is not given a priori, but whenever you give me an initial datum x0 and a final target xt, depending on x0 and xt, the minimizer is different, and therefore, right, the switching pattern will be adapted to the initial data and target, right? And this is very important because, you know, normally, as I said, when you planify a priori the switching pattern, this is like when you are, you know, making the metro, you know, planning the metro lines in a big city and so on. You can define a priori a frequency for every of the lines, right? And this you can always do so that, you know, the two trains will never pass by the same road, so to avoid collisions, right? But I mean, you can do that in many different manners. None of them guarantees you optimality, right? If you really want to make this to be optimal, you need to, you know, take into account what is the initial datum and what is the target, meaning how many, you know, users of the metro line you have and what are these destinations, right? Otherwise, if you do it in an abstract manner, you could simply do it just look into the lack of intersections, you know, along the time instances. Okay, very good. But do I need any hypothesis for this to be true? Yeah, this is something I wanted to mention, right? Indeed, I need some hypothesis. Why? Where is the trick? Where is the tricky part in this statement? I say, well, in order to do this, I need to guarantee that both, right, B1 and B2 are somehow different, right? So you have to avoid, for instance, that B1 and B2 are equal, of course, right? Because if B1 and B2 are equal, you know, this question of alternating doesn't even make sense. You say, well, you said there will be two individuals, but finally the second one never came. All the load is on me, and I have to do all the work. So B1 and B2 have to be different, but not only be different, right? But they have to guarantee that both the superposition and the difference of each of them is sufficient to control the system. It's only in this way that you can guarantee that you have really a switching pattern. Why? Where is the trick? The difficulty is not in the coercivity. Why this functional is coercive? Well, this functional is coercive simply because the maximum of the two quantities is bigger than the average of the sum, right? This is true, right? So the maximum is, of course, bigger than half of the sum. Therefore, because this sum was coercive, and this is true because of the Kalman-Rank condition, the maximum is also coercive, the full functional is coercive, and there is a minimizer. Okay. So then why do I need extra hypothesis to guarantee that, you know, that the control this leads is of switching form? You know, this extra hypothesis is needed in order to guarantee that really out of the minimization of this functional, I get a switching pattern, right? Why? Because, you know, otherwise, there could be situations where, you know, the two of them are equal, and when the two of them are equal, my argument saying, well, when this one is bigger than this one, I can simply, you know, use the first one, or when this one is equal to this one, I can use the second one, right? If they were both equal, there could be situations where, you know, I cannot decide whether I have to use one or the other, right? So in order to eliminate that situation, you need to impose that condition, right? Why? Because if the modulus of this is equal to the modulus of this, there are two possibilities, right? Either first is equal to the second, or first is equal to minus the second. But again, you can use the analyticity of phi to say, well, listen, if any of this combination is true for a say, time set, which is of non-zero measure, because of analyticity, it will happen everywhere. And if it happens everywhere, under the condition that these two pairs are controllable, right, I will be able to guarantee that this implies unique continuation, and that will be done. Okay? So this is the conclusion. So the conclusion is that you can handle switching systems in similar manners. You can do it using an a priori setup planning switching pattern. This can be done. This is no problem. But if you want to be optimal, you have to do it non-linearly. But in order to make it non-linearly, there can be, situations where, you have to avoid the fact that the cooperation can be ambiguous, right? So what this theorem is telling you is that, of course, you can much more easily plan, right, a switching pattern where, when the qualification with the kind of task that the two cooperating agents is of different nature, right? And this is again the same, when you are writing a paper, right, and you have to really, alternate in an optimal manner, right? It's much easier to do it when somehow the task of each person, right, is better identified, right? So if one is taking care of the introduction and the other one of the appendix, one is taking care of the theoretical part and the other one of the computational part, the better you allocate tasks, the more efficient the alternating scheme will be. Okay, very good. So let me now jump on into a slightly different concept, which is also very important. Is the concept of stabilization. So everything, all we did until now, right? All we did until now, what we did was open loop control. So what does it mean, open loop control? Right? It means that, I had to okay. No, this is not good. Okay, maybe take this. Okay, I had to control this system, right? From x0 into a given target, right? And then the theory we developed was, well, the UT will be given by phi star B star phi, right? And the phi, right, will be a solution of this system, right? Where phi t is the minimum of a functional j, and this functional j was an integral from 0 to t. Sorry, so here it should be, right? It should be plus here, plus a, and then here is the equal. The control was on the right-hand side. Okay, so that was the situation I was looking at. Okay. Now, people will tell you, well, but this is what is called the open loop control, right? Why is the open loop control? Well, is that, I have to go, right, in the time interval t equals 0 to t equal capital T. I have to go from, say, 1 point x0, right, x0 into a different point xt. And, in order to compute this trajectory, I have to operate on the system, right, during the time interval 0 to capital T, right? Yeah. So if I am really able to plan this, right, that is fine. This is like you are planning your summer vacation, and then you have plenty of days in order to plan it. And then you do it very carefully, and then you buy all the tickets, you buy the airplane ticket and then the train ticket, and then you book the hotel in one place, and then the hotel in the other, and then in the other, so that everything is perfectly planned, right? So you depart for, say, 1 week from home for holidays, and everything is planned. You have the car is taking you to the airport, you take the first airplane, then when getting to the airport, you take the second car, you go to the hotel, you leave the luggage, then you go to the museum, and this and this and that, and then everything is perfect, okay? But you know, if you argue that this is the way you are going to control the system, in most applications, people will tell you, well, I mean, it's good to have such a plan, but definitely you need to do something else, right? You have to be equipped by some other control device. Why? Because you say, yeah, I mean, you made all this plan, but you should take into consideration that, for instance, maybe the first flight might be canceled, or that the day you are, you know, going to the airport, right? Maybe it's raining a lot, and because of this heavy rain, right, there will be a lot of traffic jams, and because of the traffic jams, you should leave earlier home, you know, half an hour earlier. Then you have to modify your, you know, your original plan. So this idea of using purely, right, open loop control in order to control a system in which everything is given a priori, right? So the A is totally known, the B is totally known, the initial position, the final destination, everything is given. There is no any room for any possible noise or perturbation of the system of any kind. This way of controlling a system, what is called open loop, right? And in some sense, it's clear that there is a loop, right? Because the state, I mean, if you think on how I am operating, right? The X is going forward while the phi is going backward, right? In this loop, right? That is taking a time horizon 0 capital T forward and backward, right? This open loop system, you know, the control will not be able to anticipate or to adapt in case there is any unexpected event, right? In that sense, people will tell you it is much better if you are able to use feedback control, right? So this is the notion of feedback control, right? So if you do feedback control, then the question is, can I choose the control U at any time on a way that it uniquely depends on the position xt? And this is normally how, you know, people are trained to do, right? For instance, when you look to the soccer players, they are not working in an open loop fashion, right? Of course, they are trained. They have been also, you know, prepared to develop cooperative strategies to react maybe differently in different circumstances, right? But this is not part of the active control. You know, when you do this, you are somehow choosing B, you know, the actuator to be appropriate. So when you train the teams, you know, the players on your soccer team, what you are assuring is that you have a good actuator, a good B. But then how the players, right, the 11 players play in each team, you know, how the 11 components of the system are acting on real time is not given a priori in an open loop fashion, right? This will be inefficient. Actually, you see how, you know, soccer or any other sport or basket even faster, you know, the coach has to be, you know, giving instructions, taking decisions all the time. The same players that in few seconds or microseconds have to react in order to, you know, achieve the objective, to, you know, to get the goal, right? So in that case, the control is not an open loop control, right? The players they are not allowed to play again in case they see that the result after 90 minutes play is not the good one, they are not allowed to play the game again. No, no, no. You have to do it in real time. And doing it in real time, it means that there is an operator, a feedback operator, that is telling you what the control is UT, just depending on what the situation is at that time. And this is how we have to act on life most of the time, right? You get into the street, you have a plan, but then, you know, I met one person that I know for many years and I didn't see for a while. I have to stop to say hello and devote maybe a few minutes to talk to this person before I can continue, right? But because I had an appointment after I have devoted a few minutes to this person, then I have to rush, right? So I have to go faster than I expected because, you know, some of the 10 minutes I have to get to destination has been spent to talk to this person. So this is feedback control, and we are operating all the time in a feedback manner, right? Okay, so now how can I do that? Let me give you an example. Let me consider the very simplest case where, the very simple case where A is a skew adjoint operator, right? So this applies for finite dimensional systems, but also for partial differential equations where the skew adjoint operator is kind of an harmonic oscillator, right? It can be an harmonic oscillator in finite or infinite dimensions. In infinite dimensions will be systems like the wave equation, the Schrodinger equation, the Maxwell system, the elasticity system. There are many systems, you know, in continuum mechanics that also behave that way, right? When happens in the absence of control, if I don't apply any control, then if U is equal to 0, the system is simply X prime equal AX. Because A is a skew adjoint matrix, this system is generating a group of isometries, right? It's not only a semigroup, but it's a time reversible semigroup, right? And in that case, right, if you multiply the equation scalarly by X, right, and take the scalar product, what you get here, the scalar product of X prime is just half, right, of the time derivatives of the modulus X squared. You get equal to 0. Why? Because due to the, right, as indicated here, due to the skew adjointness condition, right, you get the property that AXX is equal to 0, right? This is precisely the reading, the main conclusion of the fact that A is a skew adjoint, right? So this condition AXX simply means that wherever you are, right, independent of what the dynamics of the particle is, whenever you stand here at the point X, so you see I have to do feedback because when I did this, I lost something, right? So I could not do open loop control. If I was doing open loop control, I will be talking as if my previous drawing didn't disappear, but it did disappear. So I have to write it again, right? So this is feedback control. So what I was saying is that you will be in Rn, right? And then wherever you are standing, if this is the position of your trajectory xt, right? What, the case of the skew adjoint operator, because of this null scalar product, is telling you that you are pointing, perpendicularly, right? This is why typically, right, when you are considering these, skew adjoint systems, you are defining rotations along a sphere, right? So this is the classical property of conservation of energy, in which, because simply I multiply the equation scalarly by X, and I observe that the time derivative of the modulus of X squared is equal to 0, simply because AXX is equal to 0. And because the scalar product of the the time derivative of the modulus of xt squared is equal to 0, it means that this modulus is constant. And the only thing this tells me is that, all the dynamics evolves in the surface of one sphere. You give me the initial datum. This initial datum in your Hilbert or Banach, in this case, Euclidean space, lies on a given sphere. The surface of a sphere is the norm of the initial datum, and this fully determines the surface on which the dynamics is going to evolve, right? Okay, but assume my goal was to go to 0. Then I will tell you, well, if your goal is to go to 0, you have to do something, right? Because the free dynamics, in the absence of control, if u is equal to 0, this computation was, of course, done under the condition that there is no control. If you do nothing, you will never get to 0. Why? Because the dynamics is simply rotating again and again. I don't know exactly in which direction, but I can guarantee you, just because of this conservation of energy, I can guarantee that the dynamics is evolving always on the surface of, the sphere. If you want to go to 0, you have to do something on the system, right? And this is where I need to use an active control. Now, the point is that this time, I'm not allowed to do open loop control, because although it was very pedagogic to do all these adjoints, minimization of the functional and so on, in real life, oftentimes you have to react on a real time. You cannot anticipate, you cannot plan everything, right? There are unexpected events, and you have to really act on real time in order to achieve the goal. And here, what is really unexpected is that, well, the system is purely conservative. It will go on and on and on again, right? You are expecting that there will be some dissipative effect on the system that will eventually make, generate some friction, some fatigue, right? So that the system spontaneously goes down to 0. This will never happen, because the system is designed in a perfect manner so that, this kind of, infinite multidimensional pendulum will never stop, right? It will go on and on and on and on forever. So what do I do? And the answer is feedback control, right? But the question is, how should I design the feedback operator? How can I design the feedback operator L, right? Which now it will be an operator. You see the operator L will go from Rn into Rm. Why? Because typically the control operator B is a matrix n times m, so that it takes the m components of u multiplied by b, gives you an action on the n components of x. So here, for the same reason, when I say that u that has m components has to be a function of x that has n components, right? You have to take an operator L that is mapping Rn into Rm, right? So how can I do that? Well, you see, I want, for instance, this to guarantee I am in a finite dimensional case. You know that a linear finite dimensional system, when it is stable, I mean, the trajectories go to 0, then they will go to 0 exponentially, right? Then I really like to define L on a way that, whenever you choose the control U to be Lx, then you see that actually what you are doing is you are generating a new system that I call it D, right? Where D now is the matrix A plus BL, right? A plus BL, that is, I call it D because D will be dissipative, right? So then the question you are asking me, actually, if I understand it, the question we are considering is, how can I choose L so that A plus BL is a dissipative operator, right? So how can I do that? Well, you could play again with the energy identity, and you will realize that a very good candidate for L, right? So a very good candidate for L is minus B star. Or maybe if you want some constant times B star. So why do I choose L to be B star? Well, the reason is very simple. Assume I have taken L to be minus B star, or if you want to, you can do it as an exercise. You can choose also minus a positive constant. Of course, when I say K, I'm thinking on a positive constant. You should not destroy the minus sign here. Why do I claim that taking L to be minus B star is a good idea? You can do it here easily. Why? Let us see what is the energy identity you get when you take L to be minus B star. I take L to be minus B star. Now I have a feedback control. The feedback control in this case is very smart because it says whenever you are at a given point X, right, you are applying a control, you are acting on the system in the direction given by minus B star X, right? This is what it says. It says that at any time t, right? At any time t, according to this feedback control, at any time t, u is minus B star xt. And I say, well, this is tricky, right? So where did you get this idea from? Why are you doing this? Why you are telling me that wherever the trajectory is, right, in this, say, system, in which in principle the trajectories were rotating forever on the surface of the sphere, wherefore did you get the idea that wherever I stand, xt, I should apply a control, a force, which is minus B star applied to X? Why is this a good idea? The reason is the following. Take this control, play with the energy identity by simply multiplying the equation scalarly as I did before with X. And now what you see is that half of the time derivative of the norm of X squared now is equal to minus B star XX. And this is actually minus B star X squared. And minus B star X squared is negative. So you see that immediately out of this choice, and you see why I have chosen, you see why I have chosen U to be minus B star X is because it's by taking with a negative sign U to be B star X. This is what in the duality gain between X and B star X, I get here the same B star, and therefore I get an square. Therefore, because this is a square, the square is an Euclidean norm, then I get here a negative sign. Okay? So then you see that at least you understand why I take this, you know, a damping operator. Is this damping operator sufficient? Well, I don't know. But at least it's a damping operator. Why? Because if I take U to be minus B star X, then I know that the energy now is dissipated. So now I know that, well, the tendency is towards stability, right? So the trajectories will have the tendency to contract. Now, will they contract to zero, or will they, you know, dissipate only part of the energy, but maybe eventually fall in a different sphere in which the dynamics on goes? I don't know. Okay, but at least I can guarantee that you know, that the energy, I can guarantee that the energy xt, right, that the energy xt is going down. Okay, so let me now go one step further. I would like to show, to test whether actually the energy goes to zero. Let's be more careful. I mean, this is a computation that you can do in several ways. You can do it using Lyapunov functions, hypocoercivity estimates. Let me do it in a way that I think is probably the most intuitive one, right? And in which you can better use the tools we have developed in open loop control. This is why, even though open loop control, this is like usually in mathematics, right? You say, well, you know, we use Lebesgue integration theory. But before doing Lebesgue integration, we did Riemann integration. Why we didn't do from the very beginning the most sophisticated integration theory? Well, because it's very pedagogic to first do Riemann. And actually, when you do Riemann, you understand many things, because the same ideas as Riemann are then used in numerical analysis, in interpolation theory, neural networks, and so on. Okay? Good. So here is the same. How do I analyze the stability properties of the system? Well, the first thing to do is to say, okay, let me just try to estimate precisely the contractivity properties of this semiconductor. In order to do that, what I do is I integrate this equation from 0 to capital T. When I integrate this equation from 0 to capital T, with that coefficient here 1/2, what I get is the norm at the time capital T minus the norm at the time t equals 0 to be equal to -2. I have put these two here multiplying, -2, the integral from 0 to capital T of bx squared dt. So you see, of course, the norm of x is going down. Therefore, this quantity is negative. And this is precisely how much energy I dissipated out of the system. So I am forcing the dynamics to go down, right? And then what this, quantity here is accumulating is how much energy I have extracted out of the system. This is the energy extracted out of the system in the time interval 0 capital T, right? And then my claim is that if I want to show that the semigroup decays exponentially, and this is an argument that you can also apply in infinite dimensional systems like waves and heat equations, the only thing I need to show is that the norm of the initial datum is dominated by a constant times the energy dissipated. In other words, right, what I'm saying here is that the energy dissipated represents some fixed C%, some given percentage of the initial energy, right? So my claim is that if you want to show that the system is dissipative, you have to design so that it's dissipative and goes exponentially to 0 in this case. You have to design your damping mechanism in a way that, even if the percentage you are removing of energy you are removing in every time interval is very small, it can be 1%, 0.1%, 0.01%. It can be very small, but it has to be always a percentage of the total energy of the system, right? Then you will have really a contraction and you will have an exponential decay. Why is that? Well, because if you have such a observability, and you see that this is again kind of an observability inequality, right? Because what I'm saying now, before I was working on the adjoint system, now I am working on the state system, on the state equation. But this is again an observability inequality because it's telling me that the time interval 0t, out of the projection B star, I am able to recover the full energy of the system. And this is where you see that open loop control and feedback control are very closely related. Although the idea of feedback control is much more advanced because I am controlling in a real-time manner, eventually the kind of inequalities I need seems to be very much the same. Okay, so now, before I get to the discussion of this inequality, why this inequality suffices? Well, because if you have this inequality, then when you come here to the right-hand side, you can, because of the minus sign, you can put this as an upper bound. And therefore, what you see is that, there is a contraction gamma, the semigroup from 0 to capital T is a contraction gamma with a constant gamma that is 1 minus 2 over C that is less than 1, right? And once this semigroup in time capital T, right? So the semigroup ST, right? Which gives out of X0, gives you the solution XT. Once this semigroup is a contraction, when you iterate, right, the semigroup by the semigroup property, and you simply observe how the energy in very large time evolves, you see that the energy at the time KT, right, is going to be gamma K times smaller than X0, the energy at 0, which of course you can always write in this exponential manner. The logarithm of gamma, because gamma is less than 1, will be negative, right? And K will be of the order of T over capital T. So you will get not only an exponential decay, but you will get a very explicit bound on the exponential decay, in which you see that the only two ingredients entering on this exponential bound of the decay is the gamma, the constant gamma for the contraction here, which depends on C, and the time t needed. So you see that not only I can guarantee that when this inequality, not only I can guarantee that when this inequality is true, I have the exponential decay, but actually out of the value of capital T and C, I can immediately tell you how fast the exponential decay will be, right? Okay, but now the point is, what was the system X? The system X was X prime equal a, it was, sorry, I was writing it on the other side. The system was X prime plus AX equal minus B star X, right? While normally, when we prove observability inequalities, we do it for the adjoint equation minus phi prime A star phi equals 0. But what was the assumption of on A on our discussion? We said A is anti-adjoint, right? So it means that A star is equal to minus A. And then this means that the adjoint system in that case is the system written again in the same form as the state equation without the operator B star on the right-hand side. So what does it mean? It means that if A, B fulfill the Kalman-Rank condition, the observability inequality I needed here is actually the one I know it holds for the system phi prime plus A phi, which is precisely, right, the adjoint system. So if AB fulfill Kalman, because I know this is equivalent to the observability of the adjoint system being the system itself, I know I have the observability for the system. Oh, but you will tell me, yes, but your system is perturbated by, you know, the extra quantity B star X. Yeah, but I tell you, yes, but this perturbation, right, is something that I know, right? Why? Because this is precisely the quantity that is present on the right-hand side. And then with this, you can make a, you know, a very simple argument of decomposing the solution X of the system into the phi plus a remainder. The remainder is the one given by Bx star, but Bx star, I mean, X is something you already observed. And in this way, you can easily decide that you have indeed dissipated the system, right? And this is precisely the computation that Maxwell did, right? So this is the kind of example we consider in which we have an harmonic oscillator. An harmonic oscillator is given by, you know, if you consider this harmonic oscillator, mx double prime plus rx, it could be a matrix representation. So x could be a vector, m in a matrix, and r another matrix, right? I should maybe write here capital M better, right? In this case, right, you can always write this as a skew adjoint operator, right? So just by using the classical representation n minus 1 r equal to x, so then the matrix will be 0 identity minus n minus 1 r 0, right? So skew adjoint. And this is the argument we did in the other day on the computation by Lord Maxwell to show that, you know, dissipative systems do not behave, right, really as one can expect. And you wonder, well, what is the connection of what we did here? What is the connection of what we did here with what Lord Maxwell said? Well, what I have said here is that, you know, if you revise my computation, this is an exercise, right? You will get to the conclusion that for any constant k, whatever the amplitude of the damping you take is, you know, there will be a decay rate, right? But what you know already from the computation that we did for the harmonic oscillator following the, the original contribution of Maxwell, is that you have to be careful, because the fact that this feedback, in the case under the condition that A, B fulfill Kalman and A is a skew adjoint, the fact that this feedback mechanism stabilizes the system is always true. But if you try to push your intuition in the apparently natural and obvious direction that the more K you put, the more damping you put on the system, the exponential decay of the system will be the better, then you know this is wrong. So you have to keep in mind that very often there is this saturation effect, so that when you increase the damping K, the decay rate you get here, when you increase the damping K, the decay rate you get here, which is given by this exponential type omega K, typically will do something like this. Okay? So this is the warning. Very good. Now, the theory of stabilization of finite dimensional systems evolve significantly. You can even do part of this analysis for infinite dimensional systems. And there is actually a theorem, is the pole placement theorem, right? So it's the pole placement theorem, which tells you that actually, whenever, A and B, the pair AB is controllable, then you can design, the L in the way you like, so that, the spectrum of the system is placed, right, wherever you like, so that the decay rate you get is the one you like, right? So what I'm saying here, you might think that this is a bit in contradiction with what I said before, right? What I'm saying here, I'm saying the following. If you think on the problem from an spectral perspective, right? You say, well, I had the system x prime plus ax equals 0. A was anti-adjoint. And therefore, when I look to, to the spectrum of the system on C, I know that the eigenvalues will be purely imaginary, right? And this will generate, this motion of rotation, right? So this is simply a rotating system. It's an harmonic oscillator, okay? Now, what the theory of, pole assignment says, that if you allow me now to perturb the system with some operator here, L, right, in a feedback manner, under the condition that the pair AB is controllable, right? That's important, because this is the one that allows me to guarantee that operating through B is sufficient for controlling the system, right? If I do that, then what I'm claiming is that whatever, the spectrum you give me in C, for instance, you might want eigenvalues to be now here, right? These are the new eigenvalues, lambda J, so that, they are to the left of the imaginary axis, right? And therefore, this gives you some decay rate minus omega, which is given by the spectral abscissa, the vertical, separation with respect to the imaginary part. What the pole assignment theorem tells you is that whenever you choose the eigenvalues, right, lambda J of the system for J from 1 to n, so that the real part of the eigenvalues is negative, right, then there is such an L that allows you to stabilize the system, placing the poles over there. And then I ask you, well, but this seems to be in contradiction with the phenomena of overdamping, right? What did I say? What I said was that when I take L to be of the form minus KB star, this is not necessarily the case, because I said, in this case, according to the computation that Maxwell did, what you expect on the decay rate is that it will improve for a small amplitudes of k, but then it will degenerate again. So can you please explain me why the two statements are true? Why in this particular case where, you know, the L is of this specific form, I get this saturation effect of Maxwell? And why, by the contrary, there is a general statement saying that you can always place the poles of L. I mean, you can always choose L so that the poles are wherever you like. How do you make the two results compatible? Is there a contradiction between the two results? Any suggestion? Well, of course, there is no contradiction. Why? Because, you know, here, when I made the choice of L being minus KB star, I am choosing a very specific class of feedback controls. It was very natural because it's the most obvious choice that makes the new system, the feedback system, to be controllable, to be stabilizable. It makes it dissipative, and actually I have proved exponential decay. But when I am saying that I take L to be minus KB star, I am restricting very, very significantly. I'm restricting very significantly the class of operators I am choosing. So this result of saturation for this specific class of operators is very much compatible with the general statement that says that there is such an L that is doing this. Of course, then L will be not of this particular form, right? So the comment then is that, you know, even when A, B fulfills the Kalman-Rank condition, even when you can stabilize the system, even if you can do it by choosing this very simple, natural, intuitive, right, feedback control operator, there are other choices of feedback that can be more efficient. Right, so you know, this already shows you that even in this linear finite-dimensional case, you know, finding the best feedback operator in order to control a system is quite tricky. There are many things you can do. Not all of them are intuitive, and you know, oftentimes finding the optimal policies is something that can be very tricky. And of course, this is something you see manifested also when you move into the context of neural networks and neural differential equations and the applications of machine learning, because you see all these phenomena that we are mentioning here reflected, you know, in a much more complex setting in which the dynamics is nonlinear, is finite, but can be high dimensional, is of switching nature, because sometimes you are jumping from one dimension to another, right? And therefore, you know, you could observe phenomena concerning the stability and the performance of this neural network that do not completely, you know, fit our first intuition. But when this happens, you should not think that this is something very much related to the difficulty of the neural network problem, of the high dimension of the system, of the nonlinearity, or because you are dealing with applications in machine learning that are more like fancy. No, 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 no. This is simply due to the fact that even in the classical context of a linear finite dimensional system, even though many things can be done, they are hard to be done. And oftentimes, the response of the system is not at all the one we expected. And I emphasize, this is not something new. This is something that we know from control systems since the Industrial Revolution, and that was already, you know, written down by Maxwell in the context of the harmonic oscillator. Okay, so it's a good time to stop. We can then continue with gradient descent algorithms, which is an extremely important complementary topic, both in control and machine learning area. So, okay, so the next topic I would like to discuss is extremely important in all this field of control, optimization, and machine learning, is the one related to gradient descent methods. This is a huge topic, is very classical, but there are some central ideas. We cannot cover it here fully, of course, but there are some central ideas that are very important to, to fix. And this is what I'm trying to make here, okay? So this is one of the most classical results in this context. I will discuss the motivation later, right? But so the problem is basically the following. You have a function J defined on a Hilbert space, right? You could make similar things also on Banach spaces. Let me just do it here in the Hilbert space, where everything can be written more easily, right? So you have a functional defined on a Hilbert space. It could also be Rn. You were working with finite-dimensional systems, right? You have a function J defined from this Hilbert space into R, right? And the goal is simply to minimize this functional. Right? So this is the goal, right? This is our objective. But the question is not only to, to prove that there is a minimizer. This is something we can do and we will discuss. But the goal is to really build a minimizer, okay? So you want to really write down a computer program that you can really run and see how the minimizer really emerges. You really like to know what is the minimizer, right? Right? What is X star and how does it look, right? Okay, this is what the theorem says. If you want to do this, right? So the first thing you should do is to check two assumptions that guarantee that then things are quite easy, right? And you will get a method doing this. Once you have this method, you can discuss what are other possibilities you could use that are more advanced, more efficient, faster, more stable, robust, etc. But this is what the theorem says. So you compute the first derivative of J, the gradient of J, right? The gradient of J at any point U is an element of the dual of H that you can identify, right, by Riesz theorem with itself, right? So you compare the gradient in two different points. You take the difference, you multiply by U minus V, and you want this coercivity property, of course, with a constant alpha that is assumed to be positive. So this is the strict convexity of the functional J. Okay, so this is a strict convexity condition. And the second condition is an upper bound. You say, well, on the other hand, right, I want the gradient of J to be Lipschitz, right? So basically, you want J to be C2 with a second derivative that is bounded, right? So then basically, what this is simply telling you is that you want, right, an upper bound. So here M and a lower one, alpha, right, both positive and finite, for the Herschan of J. This is basically what you need, right? And then the classical steepest descent algorithm, this is a gradient descent algorithm in which actually you are going down in the steepest possible direction, says, if you want to really to find a minimizer of J, right? So here I have denoted by U the argument of J instead of X, so maybe you should write here U, right? If you want a minimizer of J, you can proceed the following manner. You initialize the process as usual in fixed point arguments in any A0. So you take any U0 in H, In some cases, you have some guess of what is a good initialization of the process. In many others, you will simply take, U0 equals 0. This happens also in machine learning, where you are building a large neural network in order to, to approximate some model or interpolate data, right? You will do it by using some optimization, iterative algorithm. Of course, depending on how you initialize the process, you will get, much faster to the corresponding result, right? But when you don't have any clue, you just will do it either initializing the process in a random manner, right? But by, a random number generator in your computer, or you might take also to say simply U0 equals 0, and let's see what happens. In any case, this is exactly the same principle as in Banach contraction theorem. Banach contraction theorem also tells you that if you want to find a fixed point of, say, you recall, right? So you want Tx equal x. So what you do is you initialize, and then you take xk plus 1 equal Txk. If T is a contraction, right, with gamma smaller than 1, a contraction, this generates a fixed point as a limit, right? Good. So here we do the same. Of course, the same as in the classical Banach fixed point contraction principle. I mean, this sequence always converges to the fixed point, but of course, depending on how you initialize, right, it will take you longer, or it will be faster to converge, right? Because if you start from very far, you will need many iterations before you get close to the fixed point, and then by contraction, you will eventually converge, right? But if you start very far, it will take you many iterations. So the same in here. The initialization is important. But at this point, I am not discussing this. The only thing I'm saying is that independent of where you start, if you iterate your sequence in a way that in order to move from the position UK to the new position UK plus 1, you simply move in the direction of the gradient of J at UK with a step rho, right? Then this will converge, right? But in order to guarantee the convergence, you need rho to be small. You need to make small steps, right? If you make too long steps, maybe you will bypass, right? You will pass by the minimum, and rather than converging, you will get away, right? So in order to guarantee that this converges, right, you will need to make steps that are small enough. How do you measure the size of the steps rho you need to do? Well, this is completely quantified over here, right? So this is quantified by the fact that, the distance from UK to the minimizer U star, right, is bounded above by the power k over 2, of a number which is, the number here is 1 minus 2 rho alpha, alpha being the lower bound on the Hertzian, right? The minimal eigenvalue of the Hertzian of J, plus rho squared times m, m being, the maximum value, right, of the Hertzian. But you see there is a gap here. So here you have rho, and here you have rho squared. Typically, and this will depend on the conditioning of the functional J, it could be that, for instance, when you are looking to partial differential equations or systems in large dimension, because there are many dimensions, many eigenvalues, there could be a very large gap between alpha and m. So maybe alpha is positive but very small, and maybe m is finite but very large. So alpha could be 10 to the power minus 2, 0,01, and m could be 100. So alpha will be very small in many applications, and m will be very large. What happens when alpha is very small and m is very large? You need, in order to guarantee that this leads to an exponential convergence, right? you need this number here to be smaller than 1. Is this number smaller than 1? Well, it's not so clear, right? Because, you know, I have 1 minus something, so it's going down, but then I am adding something, it's going up. How does this, you know, function look, right? This is a parabola. So if I draw the parabola rho versus, you know, the value of this number, what I see is that for rho equals 0, I am starting from value 1. Then it is going down, right? Then it's going down. And then it's going up again. But of course, the way, you know, this goes down, the way it goes down, and the way it goes up depends respectively on alpha, which gives you the initial slope, and m, right, which gives you the concavity or the convexity of the quadratic parabola. Okay, fine. But you see, because of precisely the drawing I have made, the fact that, you know, given alpha and given m, you can always find a rho so that this number here, right, is less than 1. The minimum is less than 1. This is absolutely clear, right? Now, you can really, in order to compute the optimal value of rho here, you could just simply say, okay, let me just make the computation that, right? I could just simply say, sorry, how did I to add a page? Okay, I have a page here, right? So I said we have 1 minus 2 rho alpha plus it was rho square m, right? I want to achieve a rho so that this is less than 1. Well, the best I can do is take rho equal, say, rho tilde, so to minimize this function, right? This function. And in order to minimize, what I simply do is I compute the derivative of this function f of rho, f prime of rho. This is going to be 1 minus 2 alpha plus 2 rho m, right? And when I make this to be 0, I see that the corresponding rho is simply 1, sorry, is going to be, when I compute the optimal rho, this is going to be 2 alpha minus 1 divided by 2m, and this is the rho star I need, right? So this is a computation that you can, you know, complete without any difficulty, right? You can not only guarantee that this is less than 1, but you can really say what is the optimal rho for which the minimum of this is achieved, right? And this will give you, you know, in the limit, exponentially converging sequence to the minimum of U star. How do you prove this minimization property? I think I didn't put the proof here, so let me just give you the proof. In order to give you the proof, maybe I better switch to, you know, to the notes here. So how do I do the proof, right? So this is what I'm doing. I have a function at j, right, which is defined on some Hilbert space, right? I'm trying to look for the minimizer, which is somewhere in here, right? Okay, so the conditions I have are that, you know, alpha is positive, is a lower bound on the Hershon, and m is an upper bound on the Hershon, right? And I'm saying that uk plus 1 is equal to uk minus rho, the gradient of j uk, right? On the other hand, I have that u star is the minimizer of j on the space H. Because it's a minimizer, this implies that the gradient of j at u star is equal to 0, right? So what happens then? You see that, you know, because the gradient of j at u star is equal to 0, this means that U star is a fixed point of this iteration, right? Why this equation is fulfilled? Well, it's very simple. The equation is fulfilled simply because this guy is equal to 0. The gradient is equal to 0. So what I'm doing here, right? What I'm doing here is simply applying, right? What I'm doing is the Banach iteration for the map that to any u is computing, right, this value. Of course, t here, capital T, right? Capital T here has nothing to do with time. This is a static problem. This is just a minimization problem. Okay? So why I'll say this? Well, because, you know, when I do the Banach construction in order to get the fixed point of this operator T, what I'm doing out of the value of u, I am iterating the function, so I am precisely, you know, building this function. So now the question, you know, I am trying to check that I am converging to the fixed point. Why? Because the fixed point is precisely the critical point of the functional gradient j u star equals 0. So I have reduced the problem of computing the critical points of j to the problem of proving the existence of a fixed point for this map capital T, right? That's very simple. I reduce the problem of finding critical points to the problem of finding fixed points, right? So I have taken the critical points of j, now become fixed points of T. Now, how do I, you know, build the fixed point of T? I say, well, if I need a fixed point of T, the only thing I need to check is that T is a contraction, right? So what does it mean, T to be a contraction? It means that, you know, TU1, right, minus TU2, right, in norm, is less than a gamma times U1 minus U2 with some gamma which is between 0 and 1. Can I do that? Well, let's see. So what is TU1 minus TU2? According to the definition of T, there is the first part is the identity. So this is, of course, U1 minus U2, right? And the second part is given by, you know, the gradient contribution. This is minus rho, right? Gradient JU1 minus gradient JU2, right? Okay, fine. Now I have to take the norm. So rather than taking the norm, of course, in a Hilbert space, is much easier to take the square, right? Because then is the scalar product of, you know, the vector with itself. Okay, now what happens then? Because this vector is constituted by two terms, the difference of the u's and the difference of the gradients. When I compute this norm, right, I will have several contributions. The first one will be the square of the first one is u1 minus u2 squared. The second contribution will be the square of the second one, and this will be plus rho squared gradient j u1 minus gradient j u2, right, square. And the third term will be minus 2i's rho and the scalar product of the first u1 minus u2 gradient j u1 minus gradient j u2, right? So what do I have? Then I have a common factor u1 minus u2 squared, which is multiplied by 1 coming from here, of course, the 1 coming from here. Then I have an upper bound on this gradient. Oh, you remember I said that I was assuming that the gradient of JU1 minus gradient JU2 was less than m times u1 minus u2 squared. It was the upper bound of the Hessian. So here I get, you know, the m, but this m here, the m coming from here, is of course multiplied by the rho squared in here. So I have the rho squared. And then on the other hand, I have assumed a lower bound on this term, right? This was the, you know, the lower bound on the, you know, the bound on the first, the minimal eigenvalue, the convexity of the functional. So I get here, right, minus 2 rho alpha. And that's it. This is exactly what I claim. The only thing I need is to show that this number is less than 1. And of course, this number is less than 1 if rho is taken to be rho star, which is the minimum of the functional f rho, which is simply n1 minus m rho squared minus 2 rho alpha. So the conclusion is, indeed, you know, the gradient descent algorithm is converging, you know, to the minimizer. And actually the proof, once you realize that the problem is about finding fixed points for this mapping, is just the Banach contraction principle. So this is why the Banach contraction principle is so important, right? Sorry. The first time we see the Banach contraction principle, we say, well, but this is just about fixing, I mean, finding fixed points. I mean, yes, finding fixed points might be an important topic, but why so important, right? It turns out that actually nonlinear equations, like finding the critical points of a functional, is also about finding, you know, fixed points. So then you realize that, in fact, you know, Banach contraction principle appears every time you have to deal with nonlinear problems, independent of what the context is. Okay, so why I'm considering here the gradient descent algorithm, right? So why suddenly, if until now my question was about, you know, controllability, right? Why, you know, I did swap from controllability problems into, you know, critical points of J. There are many reasons for this, right? So I could give you several reasons for this. So the first one, maybe the more clear, right? So is based on the adjoint methodology, right? Why suddenly I get interested on finding minimizers of a functional J, which in principle is a topic arising in the, maybe in the calculus of variation, where, you know, we discuss these problems like the isoperimetric inequality, like finding the optimal shapes, or maybe in aeronautic shape design when I am looking for the optimal shape on an aircraft, right? But these belong to the field of the calculus of variation, optimal shape design, right? Or maybe you are just thinking on some, you know, optimization problem, right? That you address in the context of logistics, and you solve using, you know, the simplex algorithm or interior penalty method. Why suddenly, if I was dealing more with these dynamical systems problems, the controllability problem for dynamical systems, that, by the way, we have seen that allows you also to address problems like supervised learning, why suddenly I am interested on the optimization of a functional? Well, there are several good reasons for this. The first one is adjoint methodology in open loop control, right? Why? Because we said, well, even if your problem is about, you know, controlling this system, right? Controlling this system controlling this system from some initial configuration to some final one, right? What we said was, listen, eventually even though in principle this problem is formulated in the context of the, the controlled equation in which you have to build the control in order to, drive the trajectory from the initial configuration to the end. And we have seen, for instance, in these simulations, we have seen on driving the car that, sometimes the optimal trajectories are quite twisted. And this is why, getting the drive permit needs that you train for a number of hours in the, driver school, right? It's not so easy. Okay. This is not so easy to really understand at the level of the, of the direct optimal control problem for the state equation. Is much easier to be seen when you are dealing with the adjoint system. In the adjoint system, we are dealing with the adjoint equation, right? And then simply we said, listen, the problem is much simpler because it's just about minimizing a functional j dependent on phi t, right? For phi t in Rn, right? And j being, right, something in which the key ingredient was, the observation operator and plus, the crossing of, right, the initial and the final data to be controlled with the adjoint state phi. And we said, well, listen, in principle, this is kind of a complicated optimization problem. Why? Because, the quadratic form in here is given by, solving the adjoint equation out of phi t, computing the trajectory phi from capital T to 0, then observing b star phi, and then taking the square of this integral, the integral of this square. This is indeed a bit complicated as quadratic form, but we have seen that the coercivity of J, right? The coercivity of J is equivalent to AB fulfilling Kalman, right? Oh, and the coercivity of J is precisely the first condition we have imposed when we have, right? When we have set up the two hypotheses for the convergence, right? For the convergence of the steepest descent algorithm, right? The first condition we have imposed was that J, the Hessian of J, was above some alpha. And this is precisely the coercivity. So it turns out that indeed, Kalman is related to the coercivity of the S-functional, which is, what you really need to guarantee that there is an optimal, say, minimum for this functional, which leads to the control, as we have seen, being U, the optimal control being B star of phi being the minimum of this functional. And the coercivity turns out to be one of the first ingredients you need, right, in order to prove, right, that the functional has a minimizer, and that the minimizer is given by the steepest descent algorithm. Good. Oh, but there was a second condition, right? What was the second condition? The second condition was that, this has also to be bounded above. So the functional J has to be of class C2. And is this functional of class C2? Of course it is. You can do it as an exercise, right? Why this functional is of class C2? Let's see. How does the solution phi of this system depend on the initial datum? You remember we have written the initial datum, which is given here at the final time, because this is the adjoint system that we are solving in a backward manner. So how does phi depend? How does phi depend on phi t? Well, it depends linearly through this operator. So the dependence of phi on phi t is linear and given by a bounded operator. So the dependency is linear given by a bounded operator, so it is even analytic. So the dependence of J on phi t is not only of class C2, it's even actually of class CK for every K. And of course, you know, given that is given by a linear bounded operator, you know, any derivative of the functional J will be bounded above. So the fact that J is C2 in this case is just a consequence of the fact that there is a linear bounded dependence of phi into phi t. And of course, this condition here is absolutely true, right? Then you are in the conditions of the steepest descent algorithm. So then the conclusion is, oh, not only, as I said the other day, not only this idea of looking to analyzing the control property through the dual observability, inequality, and building the controls as minimizers of this functional, not only is a very interesting analytical tool, but it's actually a, you know, computational method in order to compute the control. So now I have a computational algorithm to compute the control, right? Why? Well, because I know that the control is given by this magic formula, right? Which is B star times phi hat, right? And this phi hat is given by the minimization of J. Now, if you tell me, well, I need now the minimum of J, I'm not satisfied by simply knowing that there is a control. I need to compute the control. Okay, if you need to compute the control, then it's very simple. So take any initialization, say phi 0, right, which is given by some initial guess you do of phi t, and then iterate this so that phi k plus 1 at any time, right, in any case, sorry, is given by, you know, this gradient in the previous step. Then you iterate for k, you know, larger and larger and larger, and you know, right, that this converges, right, to phi t, which is the minimum of J, and therefore it converges to the control, right? Therefore, you know, whenever you make an iteration here, you compute the corresponding, say, control, and you will be getting closer and closer and closer to the control. So you see that I have built an algorithm that not only, you know, guarantees there is a minimizer, but actually, you know, I have also given an algorithm to converge to the control. By the way, I didn't say...
Hi, Professor.
Yeah?
This is just the terminal value, right? You should solve the backward ODE, then use this B star.
Right. Yeah, so this is a very good comment, actually. So what we are doing, we are taking the forward equation, right? We are taking the forward control problem in which the goal was to get to xt, right? And I want the control U that is able to do this, right? But this control U in practical applications, if you are dealing, you see, when you are dealing with a very large, for instance, network system, in which the dimension of the system is very large, even if I tell you that because of the Kalman rank condition, the control exists, it is very hard to compute. It's a very tricky thing. So what I am offering you is here an iterative algorithm. And what is the iterative algorithm I am offering you? I'm telling you that you should, you know, out of, you know, this iteration I have written for the minimization of J, you should simply, you know, keep improving the U, right, by taking UK to be B star phi K. This is my suggestion. You just take UK to be B star phi K. Now, how do you compute the phi? Indeed, I mean, this is a good point. How do I really iterate on the phi? Well, what we have written, if you make it more precise, and this is very interesting indeed, so that you can really, you know, program this in your computer. You take the adjoint equation, right? Right. That for which you are given some final condition. And as you said, so here I have to solve the equation from t equal, you know, capital T to 0 in the backward sense. But now this is fine. This is just an ODE that I have to solve in the backward sense, but I can just, of course, in analytically, I have a representation out of the exponential formula. Of course, this is not what I will use in practical applications. In practical computational applications, I will just use some time discrete version for this equation phi, right? But then what I do is the following. I say, okay, I initialize this with some phi t equal to some initial guess, let's say phi t0. So this is the initialization. If you don't know what the initialization should be, as it happens very often, you just take, for instance, phi 0 to be 0, then the algorithm reads, take phi 0, the initialization you like, for instance, phi 0 equals 0, solve this equation, right? Solve this equation, and then correct the guess you had of the phi, right? Correct the guess you had of phi, by, you know, correcting the one you have with the direction of the gradient. So what are we doing in practice? If you check, what we are doing in practice is extremely intuitive, right? This is actually what we will do if we didn't know mathematics, we didn't know how to handle this. This is what we will really do in, you know, in the practical experiments. So what do? We say, okay, right? You take the original system, right? And you told me that I should test the control. Of course, you need some mathematics to know this, because someone has to tell you, well, check the control given by, you know, UK equal, you know, B star phi k. You will plug this into the system, and then you will realize that you will get, of course, a trajectory sk. And when you check whether you are exactly at the final location, you will realize there is some error, right? Because this is an iterative process, right? So in principle, the steepest gradient descent, we said it converges exponentially. There are other variants like, you know, the conjugate gradient that in finite dimension converges in a finite number of iterations. But here I am just considering the steepest gradient descent algorithm, which according to Banach contraction needs infinitely many iterations to converge. Of course, I mean, we don't need in practice to do infinitely many iterations, because I will be satisfied as soon as the error here in a practical application, I will be satisfied as soon as the error is sufficiently small. For instance, when I'm coming home, right? You know, I don't need to get exactly to a given point on the entrance of home. The only thing I need is to be in front of the door to be able to get in, right? So the error I have here will be the 1 meter width of, say, the door, right, of home, or the 70 centimeters width of the door to home, right? So you don't need exact control. You just need an approximate control with an error that is small enough. And what the steepest descent algorithm tells you, this error goes down to 0 exponentially. So in a finite number of iterations, not that large in practice, I will be really where I need to be, okay? Now, what is the gradient system doing? Well, the gradient system is saying, okay, so once you had a previous iteration for the adjoint, because of the error you have observed here, what you will do is to correct, right? You will now go back to the adjoint, right? And then in the next iteration, what you will do is take the value of the adjoint you have, correct it with the error you have done now, and compute the new phi, right? So then in practice, what we are doing is we are iterating, right? So what we are doing is we are iterating on phi, on the index k. We are iterating on the index k for k greater than 0, a process in which we take first, you solve the adjoint system, right, out of some value, right? Phi t. You solve this system from capital T towards 0. Once you have solved this adjoint system, you go to the original control system, plug in this control, right? Now you have to compute the system in the forward sense, because now for the control problem, you have an initial value problem with the guess of the control you did in the iteration k by solving, right, the adjoint system. Once you get to destination, you check how big is the error you are left, right? And with this error, right, you come back to the adjoint system, right? With this error, you come back to the adjoint system, right? And correct, right, using the gradient descent with a small rho in the direction of the error. This is what we are doing. So you are generating a loop in which you solve first the adjoint equation, plug the adjoint solution into the state equation, you solve forward, you see what is the residual, the error on your objective that was get to the terminal destination, and then go back, you know, with the adjoint by correcting the departure point in the direction of the minimizer of the functional J, right, in the steepest descent algorithm. So you see actually that, you know, the fact that the error on the destination, on the final objective of, you know, controlling the system has been reduced to actually, you know, iterate, right, on the value of the adjoint state at the terminal time, right, so that the phi at time capital T is going down, 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 down to the minimizer of the functional J, right? So this is how the algorithm, and this is what you can find in our, you know, the toolbox of the DICON European Research Council Advanced Grant. I have shown you the other day the toolbox, DICON control toolbox. This is what the toolbox does, right? So it will take, you know, adjoint system, solve forward, plug it into the system, right? Sorry, solve in the adjoint system backward, plug it into the control system, solve forward, compute the error, and when the error, you come back, and then you are simply implementing a gradient descent algorithm, okay? So this is the interest of this, you know, adjoint methodology, right? So we have seen that the adjoint methodology for control right? It has the following properties, right? It reduces the control problem to minimizing J for the adjoint system. Right? Good. As we have seen, the minimization of J can be handled by the direct method of the calculus of variation. So the existence of the minimizer, right? So the existence of the minimizer, the theoretical existence of the minimizer can be handled by the most elementary methods in the calculus of variation, right? Under the observability condition, which turns out to be equivalent to AB fulfilling Kalman. So you see that we have a full characterization of the controllability according to Kalman. We knew this, but now we have made all these to be interpretable in terms of the adjoint. And the existence of the control is guaranteed just by applying the direct method of the calculus of variation. But not only this, right? Now the next point is that, you know, thanks to the gradient descent algorithm, right? We have made, you know, the search of the control, right, becomes algorithmic, right? Algorithmic in the sense that the only thing I need to do is to, you know, solve the adjoint equation, plug the control given by the adjoint equation in the state equation, and then correct, right, according to the residual, and do a loop in which I do adjoint forward, adjoint backward, right, adjoint forward, adjoint backward, in an iterative manner, right? Very good. Of course, then in practical applications, when you are doing this, you have to pay attention to the computational cost, right? Because we have seen that, yeah, we have to iterate on K. But every time I do an iteration of K, in K, I have to solve the backward equation and then the forward equation again. So every time you do an iteration, you will pay the price, right, of solving the backward adjoint equation and solving the forward state equation. So you see that when the time horizon is very long, right, when the time horizon is very long, and the dimension of the system is very large, right, this could be computationally expensive. Right? So what we are saying here is that all these algorithms converge. Yes, they do converge. But what is the computational cost? Well, this is something that you have to analyze separately, because when you increase the time horizon, right, you increase the dimension of the system. You know, the properties of this matrix in terms of dispersion become worse. Then the numerical algorithm will have to take, you know, the time step on the discretization of this ODE will have to be smaller and smaller. Then the computational burden, I mean, the computational weight, the computational cost of this algorithm will increase, right? So we have to, you know, be careful. What we are saying here is that we have a good analytical understanding and we can build algorithms that they are converging. But of course, depending on the complexity and the size of the system, you know, how long you need to make this algorithm converge might become an issue. So for instance, people that are working with, say, Navier-Stokes equations, they will tell you, well, I mean, if you are trying to do a real, say, simulation for, you know, the Navier-Stokes equation, it takes minutes, it can take hours on your computer, right? When you are dealing with some three-dimensional real scenario. So it could well be, you see the complexity of this computation and the complexity of the backward computation for the adjoint is nearly the same. It could be that, you know, when you are dealing with real applications, every iteration K, right, in this loop can take a substantial amount of time. So then in practical applications, you are not allowed to do as many, iterations of K as you want. Even when that happens, this is a very efficient method. Why? Because actually we are doing what our intuition says. Our intuition says that whenever you have to control a system, right? Whenever you have to control a system, if you were not successful, if you implemented a control and there was some residual left, and this is something that will happen always, because whenever you try to control a system the first time, you will not get to the real target. You will get maybe close if you are lucky. This is like, these golf players, right? So they kick the ball maybe 200 meters away, and it's very unlikely, that the ball will get into the golf hole in one shot. If you are a good golf player, the ball will get close to, but there will be some epsilon. Of course, if in the first kick, the epsilon is very small, maybe you are lucky and you do it in the second shot. It's very important to make the epsilon small, right? But in any case, what is even more important is that wherever the epsilon is, you know how to get closer to the target. And what this method is telling you is precisely how to do this. The method tells you whatever error you get, if you want to correct your control, you have to improve the guess of the adjoint. And the way you improve the guess of the adjoint is by solving the adjoint equation again with a target, with a final value, capital phi t, which is, diminished according to the gradient iteration rho epsilon k. That's the key idea, right? Otherwise, if you will be in such a context in which you have taken the control system for X, you have applied a control, and you have realized that there is some error, your question will be, oh, and now how do I improve my guess of the control? I see I have an error, but there is not an obvious intuition at all of how you have to, modify your search of the control U out of this error. What this adjoint methodology tells you is, indeed, you are right. This is not obvious at all. Because the way you have to improve the U is through B star phi. Therefore, you have to improve the phi. Improving the phi is not easy because you have to solve the adjoint equation again. And then the impact on the distance to the target is precisely the one you have to impact on, the initial guess at t equal capital T on the adjoint, right? So finally, intellectually, this is not so complicated. But in a practical application, if you didn't have such a methodology, it will be really impossible to improve the, the initial guess of the control. And this is precisely the duality of Wiener between control and communication. They go together, and here you see it. Even when you are dealing with these linear finite dimensional systems, if you try to operate in an intuitive manner, your intuition fails because there is a point where you say, well, I have an error, but what does it mean in terms of the improvement of the control? You see that when you write this gradient descent algorithm on the adjoint, you can have a very precise formula of how you have to do it. But it's never easy because you have to go through the adjoint and correct actually, your guess at time capital T for the adjoint. Good. Thank you for your question. Now, this topic is, of course, very rich, right? Because we said, I have, formulated the problem of minimizing a functional J on a Hilbert space. And we have already observed a number of things, right? So one of them is that the direct method of the calculus of variation gives me, you know, conditions to guarantee the existence of the minimizer, right? So these conditions are, I remind you, these conditions were basically, you know, H to be a Hilbert space. It could be also reflexive. J to be continuous, right? J to be convex, and J to be coercive, right? Which is the fact that the limit as you goes to infinity norm of J is equal to infinity. So basically what I'm saying is that, you know, the functional I am considering J, right, has a graph of like really a nice, you know, convex coercive functional that will definitely then reach the minimum over here, right? This will be the minimum of J. Good. Okay, so this is the theory. Now, what we have done is that using, you know, a steepest descent, we have built an algorithm, okay? And all this can be interpretable or can be interpreted in the context of control. By the way, maybe I didn't justify, why do I say that this is the steepest descent? Well, the reason is very simple, right? Because after all, we were trying to minimize the functional J. What I'm doing with the functional J when I am iterating from UK into UK plus 1? Well, I am, you know, if I will apply Taylor expansion, and I see how the value of J is evolving from UK into UK plus 1, then what I see is that according to Taylor, because UK plus 1 is given by UK minus rho gradient JKU, then I have that this is JUK, and then I have minus the variation, which is, right, multiplied by the gradient of JUK, right? So you see that indeed by taking, you know, the correction of UK in the direction of the gradient, I am really, right, I am really minimizing the most possible, right, the value of J. This is going down, right? Do I really need to use the gradient as a descent to go down? No, I mean, I could take other directions, right? So I could take other algorithms, other descent algorithms like UK minus rho, and then I could put here delta K. And then if you ask me, what do I need about delta K to guarantee that the algorithm is going down? I will tell you, well, this is quite easy. I write down Taylor again, and then I will have this times the gradient of JUK. So I will tell you the only thing I need in order to guarantee that this is a gradient descent algorithm is that, sorry, this quantity to be positive, right? As soon as this quantity is positive, I will be able to guarantee that I am going down. So it means that if the gradient of the functional in my Hilbert space, the gradient is pointing in this direction, right? I will tell you, well, you need a, you know, you need a vector delta, right? You need a vector delta that has an angle of less than pi over 2 with respect to the gradient. I don't really to be pointing in the direction of the gradient. If you tell me that the direction of the gradient is the one you like, I tell you, doesn't really matter. You can take other directions under the condition that this angle, right, theta, is less than pi over 2. That's the only thing you need. Okay. Why do we call a steepest descent? Well, because, of course, among all the possible directions delta that, you know, make the scalar product of the gradient positive, of course, the most favorable direction is the direction of the gradient, right? Okay, good. Of course, when we say that this j uk plus 1 is equal to this minus this, oh, I am forgetting the error, of course, associated, you know, to the quadratic terms, right? And is when you look to the error that depends on the Hessian of j, that you realize that in order to guarantee that this is really going down, you need rho to be small. And this is what we have done in the proof of the steepest descent algorithm. Okay, but the idea, the geometric idea is very clear. The gradient of j is always the direction of descent, which is the steepest one. Now, if you don't want to use the steepest one because, you know, it cannot be implemented in practice or is computationally too expensive, you can make something that is, you know, like here, right? Oriented in the same direction, but not necessarily the same. So this is, of course, important in applications, right? Because as I said, when you are applying the steepest descent algorithm, right, you need to compute, you know, again and again the solution of the adjoint system, right? And then if we were, you know, solving the forward equation with a mesh, right, this is, you know, this leads to these algorithms which are of two-grid type, right? In order to track the dynamics of the physical system, of course, you would like to take a delta t, which is quite small. Good, because, you know, we need a good approximation of the dynamics, right? I'm tracking these dynamics. I'm, you know, I'm dealing with, you know, a ship, you know, navigating, you know, traveling along the sea, right? I have to track it well. Or I am dealing with a problem in more social sciences, you know, tracking the opinion of a society or tracking the, you know, the propagation of some epidemics, right? I'm, you know, have to make it very carefully. This is the dynamics I am interested, and therefore I will really do it carefully, right? But then if I take delta t very small, right? When I come here to, you know, the application of the gradient descent algorithm, I will realize, yes, but you see, if I take here delta t very small, and this is something I like to do because I want to have a very good approximation of the physical dynamics. When I come here to the adjoint equation, this will be delta t very small as well. And this means that every time I will solve the adjoint equation, this will be computationally very expensive. And then if you ask me, Enrique, can you offer me an algorithm which is cheaper? I will tell you, well, listen, if you really want the steepest descent algorithm, you have to keep the same delta t. But what we have observed here is that, you see, in order to guarantee that you are going down, you don't need to point in the direction of the gradient. Any direction which is close to the gradient guarantees that you are going down. So if you really want a cheaper algorithm, right, what you can do is the following. You can take delta t, right, here, right, in the adjoint. You take, you know, you take a new delta t, right, which might be, for instance, you know, 2 delta t or can be 10 delta t. What is the bonus of taking a delta t on the adjoint which is bigger? Of course, now when you are solving the adjoint equation, you will go much faster, because now, you know, you will be jumping, you know, in blocks, you know, from capital T to 0 in much fewer steps. So, okay, and then if you tell me this, I will say, oh, that sounds interesting. I am, in the forward equation, I keep the same delta t because I need to be precise. So in every iteration, the resolution of the forward system will still be expensive, but at least the resolution of the adjoint system will be cheap. Is this justified? And the answer is yes. This is justified. Why? Because at the level of the gradient descent, I don't need to go always in the direction of the gradient. I can relax this a little bit and be in a direction which is close to the gradient. Now, of course, you cannot exaggerate, right? Because if here you will take, the new time step to be really too large, then what could happen is that, the direction in which you are pointing is not anymore, right? Is not anymore in a small angle with respect to the gradient. And then if you take this direction wrong, right, so that, delta k times gradient of uk is not positive but becomes negative, then this will be the wrong direction, and rather than going down, you will be actually going up, right? So there is a limit on this idea. But this idea is something that is implemented systematically and is the two-grid idea. So you need a grid which is fine for solving the forward system because this is the actual dynamic you are interested in. But you can use a coarser grid in order to compute the approximation of the control. Will this be the optimal algorithm? Well, it will not be the optimal in terms of the descent because the steepest descent, as the name indicates, goes faster down, right? But it will be better in the sense that you will reduce the computational cost. And of course, in practical applications, you have always to keep this balance, right? Between computational cost, right? And efficiency on getting to the minimizer. Very good. So as I said, this is a fantastic topic. There are connections with many other areas, right? So we have seen connection with the calculus of variation because, a steepest descent algorithm is a way of doing algorithmic, the problem of finding, the minimizer of a functional. We have seen that actually the proof is just a Banach contraction, very simple. But we have seen also that when you apply this to control problems, it's very tricky because the Kalman run condition is hidden there, right? All this is, very rich. Now, if you show this gradient descent algorithm, to someone looking to dynamical systems, they will tell you, well, you see, all these looks very close to a dynamical system, right? What is the dynamical system that is hidden on this equation, on this discrete iteration? Oh, yeah, that's a very good question. Is rho constant in practice? I mean, that's a very good question, right? So, thank you, Cheche. So, is rho constant in practice? Well, in practice, of course, you can make rho to evolve also with respect to k, right? So here, when I formulate this with the steepest descent algorithm, I'm being conservative, right? You remember? Because I have chosen rho to be what? I have chosen rho to be universally valid, right? So the way I have chosen rho, it was because I needed, what was the formula? I think it was something like, I needed 1 minus 2 rho alpha plus m rho squared to be less than 1, right? That was the condition. But here, when I am, doing this, I'm just using the upper and lower bound on the Hessian of J everywhere, right? So this is a very conservative way of doing. Analytically, this is the, the way to prove that the gradient descent algorithm converges. But of course, if you are, when you are doing it on your computer, you will never do it that way, right? Because, you know, as we have seen, right, rho, right, has to be small and is of the order of alpha divided by m, I think it was, right? So you say, well, this is very small. I mean, typically, if you will take a, you know, an ill-conditioned, and this is related to the conditioning of the minimization problem, right? If you take an ill-conditioned minimization problem, in which, you know, typically, for instance, J, right? If you will be solving a problem like, you know, when you are solving a classical application, is just solving a linear system, mx equal b. Of course, I know the solution is x equal to n minus 1b. But assume that m is definite positive, right? And symmetric. In that case, I can write down, right, x as being the minimizer of the functional jx, which is 1 over 2 mxx minus bx, right? Do it as an exercise. Show that solving this linear system of equations, and actually this is what we do also in partial differential equations when we say that I'm solving the Laplace equation using finite elements, last milligram, and so on, by making the problem to become a minimization problem, right? When I say this, then I realize that, of course, in terms of the, right? Oh, maybe M was not so this should be a Goric M, right? Goric M to distinguish, this is the matrix, to distinguish it from, right, the upper bound. You see that the conditioning of the matrix is what determines the speed of convergence of the steepest descent algorithm. So because if the smallest eigenvalue of m will be alpha very small and the largest eigenvalue very large, this number, right, so this is the condition number, will be very small, and therefore the progress of the steepest descent algorithm will be very small, right? Now, when you are doing it in a practical manner, of course, you will take rho to depend on k. Why? Because you see, I go back to the Taylor expansion I was doing before, right? What do I need? If I say that, right, I do the Taylor expansion, then I allow myself a variable, right, a step. And then if I want to analyze which one should be really the right step to take, you will go to the next term on the Taylor expansion, and then you will get rho k squared over 2 divided by 2, right? And then you will get the Hessian of j at uk, right? Apply to gradient, you know, uk twice, right? And then you realize that the optimal choice of the rho k depends actually on the location you are on UK, right? So then in practical applications, you will never do, or very rarely will do, except in very elementary cases, choose a rho which is constant. I mean, this is done just for analytical presentation of the key ideas. But in a practical application, you will optimize the rho k, and there are many rules how to do this using the Hessian, but of course the Hessian is hard to compute. Then you will do it with an approximation of the Hessian, and the approximation of the Hessian, you can do it comparing the gradient in different, say, time steps, right? Or you can do some Armillo rule in order to guess at least some improvement of the rho and so on, right? So there are many variants of the, say, thank you for your question. There are many variants of the steepest descent algorithm, which are simply based on the fact that in every step of the descent iteration, you will choose a different rho, so to push the method faster, right? That's totally true, right? But from an analytical perspective, really, I mean, already the gradient descent algorithm, as I was about to say, is very interesting. When you show this equation for someone that is doing dynamical systems, this person will tell you, well, but this is just, I mean, this descent algorithm that you are formulating as a analytical tool to minimization and optimization problems. And therefore also as a corollary of all these duality approximation to controllability, right? Through Kalman and so on, for solving dynamic control problems. This, to me, it looks very close to also a dynamical system, right? Because the dynamical system here is this, right? Yes. So here, I'm not doing numerics. Here, I'm just solving a gradient system, right? So maybe in some Hilbert space, right? Do you see the analogy between this gradient dynamical system and, you know, the iteration we are writing in order to minimize the functional J from a numerical optimization perspective? Do you see the link? What is the link? Assume you were a dynamical system person, right? Dealing with such a system motivated by some application, whatever, the meteorology, fluids, you know, particles. You have to solve this. How do you do it numerically? Well, the simplest way of doing this numerically will be to say, well, let me take a time discretization, right? So I will say that UK plus 1 minus UK divided by delta T will be the gradient of J, right? If I do the Euler explicit discretization, this is what I get, right? Okay, so, and if I make this Euler explicit discretization even more explicit, what I realize is that then UK plus 1 is simply, right, given by this. So you see that actually the steepest descent algorithm for the minimization of J, which is actually just computing the critical point of J, where the gradient of J is equal to 0. That in the case of convex functionals, under the condition that we have the coercivity alpha and the upper bound M, was solved using, you know, Banach iteration and blah, blah, blah. This is just about, you know, like time discrete versions of these dynamical systems. And you say, well, I mean, that's interesting. So, you know, it looks like, you know, there is a link also between the behavior of this dynamical system and the fact that, you know, we are building efficient algorithms to minimize the functional J. Why is that? Well, as you know, there was someone, you know, like at that time, people like Lyapunov, Poincaré, etc., that indicated, listen, you know, the classical theory of ordinary differential equations or partial differential equations was very much about finding explicit solutions. And then there was Cauchy who said, you should stop doing this and try to deal with the general problem of existence and uniqueness. And then there were people like Poincaré and Lyapunov who went even farther and said, yes, but you should not only look to existence and uniqueness, but you should also carefully analyze the quality behavior of the solutions, because, you know, you can have existence and uniqueness, but it's very different to have a dynamics that is periodic or quasi-periodic, or is diverging to infinity, or is you know, converging to some steady state. So, and then in order to do that, you have the concept of Lyapunov function. What is a Lyapunov function? A Lyapunov function is a function that is going down along trajectories, right? So Lyapunov said, if you are able to, in your ordinary differential equation, find a functional that is going down along trajectories, this is very helpful for you to understand how the trajectory is evolving, right? Because you know it's going down, right? Okay, so if you tell me that someone has taken the elevator down, then you wait for this person on the basement, right? Because you expect this person to come down. So this gives you a very clear idea of where you should try to meet, you know, the destination of these other people you are waiting, right? So is there a Lyapunov function in that context? And the answer is yes. What happens when you know, if you think that this is evolving in a Hilbert space, then of course you have the scalar product in this Hilbert space. How can you build a Lyapunov function? It's very simple. You take the equation here and you multiply this equation scalarly by the derivative of u itself. Assume you have a solution. So by now I am just doing heuristic. Assume there is a solution. You need, of course, conditions on this gradient of J, you know, to have a unique solution, right? The simplest will be you assume that the gradient of J is a Lipschitz function on the Hilbert space. Good, then you have a solution. Then my claim is multiply this solution by u prime of t. What happens then? Well, so here to the left, I will have, of course, the modulus square of u prime of t. To the right, I will have minus u prime of t multiplied by the gradient of j at ut. And when you see this, what do you identify in here? How you can rewrite the scalar product of the derivative of u prime t times the gradient of j ut. Do you see a compact way of representing this? Well, this is actually minus the time derivative of j ut, right? Because if you apply the chain rule, when you apply the chain rule, the time derivative of j ut will be the gradient of j in ut multiplied by u prime of t. So this means that for these gradient systems, the functional j is a Lyapunov function. Why? Because, you know, j ut, the derivative is minus u prime t squared, right? So why? Because it's the derivative of j ut is minus u prime of t, which is non-negative, right? And this is what it leads to the Lasalle's invariance principle, right? That says what? It says, listen, if you are solving this dynamical system, you have for free a Lyapunov function, which is the functional j itself. What is the trajectory ut doing? The trajectory ut, right, is evolving, maybe very complicated, but you know that, you know, the level set of j on which ut is living is always going down, right? And you see, the only way you can stop the process, is that u prime is equal to 0, right? Of course, if u prime is equal to 0, then the derivative of j is 0, and then you can stabilize on a given level set. But in order to stabilize on that level set, you need u prime to be 0. But when u prime is equal to 0, so it, you know, the Lasalle says the process will only stop when, you know, u prime is equal to 0, which means that you are on a critical point, right? Because if u prime is equal to 0, then u prime to be 0, you know, the gradient of j has to be 0 as well. Therefore, you are on a steady state, right? Of course, you know, when you want to make these, you know, statements of Lasalle rigorous, you need some further conditions. But this is, for instance, what happens when, you know, you are considering now in a Hilbert space, you know, a process like this, right? So a process generated by a functional j, right? Okay, so let us consider this case. And then I ask you, so here you see there is a local minimum. So this is maybe U1. There is another local minimum U2. And then there is a global minimum, which is U3, right? Okay, so you see, of course, J is non-convex here, right? So it's non-convex, right? So we are in a more general scenario, not necessarily in the simplest case of the controllability of a linear ODE or the minimization of a nice convex function. The functional can be non-convex. And now you say, well, because this link you discover with dynamical systems, what I do is I set up this dynamical system, right? So this is like when you go to this, swimming pool, water parks, where there are many swimming pools and toboggans, and then families are playing, jumping, going down and up, and all kind of water games, right? This is one of these places, right? And then there are different, say, swimming pools where you can play the game, right? So you can game here, here, or here, right? Okay, so now I ask you, I initialize the dynamical system from here. So, you know, in here. If I solve this dynamical system, right, with an initial datum for the Cauchy problem, right? So there is always an initial datum for the Cauchy problem. If I take the initial datum in here, where do you think that the dynamics of this gradient system now will lead me? What do you think is going to be the limit of the trajectory of this gradient system when I start from an initial datum, which is placed here? What do you think the limit will be? Oh, U1, says Cheche. This is right. Why? Can you tell us a hint? Why is going to be U1? Yeah, very good. Cannot, yeah, Han, Yao Yue Han is telling us that it cannot come out of it. So can you explain me why, for instance, sometimes it's happened, right? So if I will have a lot of, say, inertia when heading here, maybe I could hope that I can go up and then come down again and then come up, and maybe I hope to get here. Will I be able to do it along this dynamical system? No, I cannot. Why? Yeah. Yeah. So yeah. No grad uses stochastic gradient. So thank you. That's a very good comment indeed. So you see, if you just do the gradient dynamical system, which is purely deterministic, if you start from here, I tell you, you will converge to this point, to U1, right? You will converge here. You will come like this, right? I'm sorry, you will never be able, starting from here, to get here or to get here. You will end up here. Why is that? Because we have seen that with this gradient system, the level set J of U goes down, right? So you are going down. Therefore, if you started from this point, this is the level set you have. And the level set along the trajectory is always going down. And because it's going down, your trajectory will be immediately trapped on this well. You will never be able to come out of this valley. And you say, well, is it true? is there no chance that I get maybe here? So why I cannot get here? Well, because this trajectory is continuous. If you want to get here, you have to pass by here. And if you pass by here, then you look to the value of j, and the value of j is higher. But j, according to the Lyapunov functional j that is going down, we know that j is always going down. So by contradiction, you will never be able to escape from this valley. And then if you now start the process in this other point, then we see immediately what is going to be the limit, right? The limit will be U2. And when you start from this other initialization point, then yes, the minimum will be, U3. So this is extremely interesting because, of course, it tells you that for nonlinear, of course, in such a case, right, the system is not linear anymore, right? So this is a nonlinear system. This is not a linear system. Why? Because if this was a linear system, the j will be quadratic on U. And if j is quadratic on U, you will never generate this kind of, twisted dynamics with several valleys, several wells, right? So this then leads to a nonlinear dynamical system, right? Then what I am saying here, well, the asymptotic behavior of nonlinear dynamical systems can be complicated. It can be understood also with these tools, or these tools can help you understand. But please don't expect something naive and simple that every trajectory will go to the same steady state. Different trajectories can converge to different steady states. Each of the limits will be a steady state, but it will be a different one. Okay, very good. So on the other hand, can this be used can these algorithms be used in order to, if you forget about the dynamical systems, just about minimizing functionals? The answer is yes. But normally when you apply the steepest descent algorithm, you will get to local minimizers. And if you really want, if you started at this point, and you wanted to get to the global minimizer, you can never do it just by a steepest descent, because you will be trapped always on this, local well. If you want to be able to get there, then you will have to explore other universes. And then in order to explore other universes, you will have to combine your steepest descent algorithm, which is fully deterministic, with the possibility of, reinitializing the process by some other random search, right? So then, you will add randomness to the process. And I finish here by saying, well, I will suggest then that you do, right, a steepest descent algorithm. Well, of course, as we said above, possibly improving locally the step to go a bit faster, not to be bounded by the worst case scenario. And then I say, well, once you have done this step, so maybe you can allow yourself some, small variations of UK plus 1 that are, add some random effect, right? Because then, what you will be doing is in every time step, you will be improving your guess, but also allowing yourself to, if you are lucky enough to jump into another well, then, if the J of UK plus 1 plus RK is less than UK plus 1, then in your iteration, you will replace UK plus 1 plus this new well that you have discovered that is deeper. If not, continue with UK plus 1. Okay, so this is something, of course, as soon as you will have the feeling that your minimization problem, and in machine learning, when you are dealing with neural networks and so on, they are never convex. As soon as you have a you know, the feeling that your function that you are minimizing is not convex, is always good to make a combination of a steepest descent, gradient descent, very much inspired on Lyapunov systems, plus a little bit of randomness. Okay? So thank you for your attention. We stop here.